We are now ready to describe what all constructible numbers look like in terms of towers of field extensions. There's just one little construction we need before we can put all this into motion, and that is the following: that if you can construct a, then square root, you can also construct square root of a. So let's call it a lemma maybe. If a is constructible, then square root a is constructible. And how does this construction work? Well, let's use GeoGebra. So to start with, I have the segment OA of length 1, and I mark off to the left of O another segment of length A. And now I'm going to construct a segment of length square root A. So firstly, what I do is I find the midpoint of A and B. Let's call it C. So this we can do again using straight edge and compass. I already did this when we were trying to find construct square root of 2. So we find the midpoint and then we draw a circle. I'm only drawing half of it here with center C passing through A and therefore also B, because C is the midpoint of AB. So we construct this circle C, and through O we construct a perpendicular to the line that passes through OA and B. And then let's call the intersection of this new line with the circle D, with the circle C, to be capital D. And now you look at you join the line segments BD and you join the line segments DA. I don't really need to do this, but I'm doing it to explain to you something. So now you look at these two triangles, ODB and OAD, in that order. These are similar triangles because I guess it's easy. This angle here at B and this angle here at A, they add up to 90 degrees. And so that shows that this angle here at B is the same as this angle ADO is the same as angle DBO. And so these two triangles are similar. Now, since these two triangles are similar, if I take this length OD and divide it by A, that is the same as 1 divided by this length OD. And so this length OD, it cannot be anything but square root of A. Okay, so having constructed A, we can also construct square root of A, as this construction shows. Okay, so that's the proof of this lemma, and let's move on. So the other thing we need to do is to be able to construct a coordinate system. This will be convenient because right now what we have said is that a constructible number is the distance between two constructed points. And you may have a lot of constructed points floating around. It's difficult to keep track of what are all the constructible numbers that you have created so far. So we'll create a coordinate system. And this we can do with straight edge and compass. I'll just do it by hand here. So you start with your line segment OA. And then you can draw a perpendicular to it using straight edge and compass. So firstly, in fact, maybe given OA, you can draw a line that's the x-axis as just the infinite line that passes through O and A. Oops, I need to move it up a bit. Okay, so this would be my x-axis. And for my y-axis, I'll draw a line. So let's just remember where OA was. This is OA. And for the y-axis, I'll draw a line perpendicular to it, which I can also construct by straight edge and compass. And now if I have any point P, then I can drop a perpendicular from P to Y to the y-axis, and I'll call this P subscript Y, or just little y. and I can drop a perpendicular to the x-axis, and I'll call this p subscript x. So we can always construct, given a point, firstly, given O and A, which were given at the beginning of our construction, we can construct a coordinate system. The x-axis is the line that passes through O and A, the y-axis is the line perpendicular to it. And if we can construct a point P, then by dropping perpendiculars, we can construct the x-coordinate and the y-coordinate of P. Okay, so we can mark off a distance equal to the x-coordinate of P and a distance equal to the y-coordinate of P along the x and y axes respectively. So, what we observe here is that, maybe I'll just call it an observation. If P equals x comma y is a constructible point, then x and y are constructible numbers. But also, if we can construct these distances x and y, then we can mark them off along the x and y axes and draw perpendicular lines. We can draw a line perpendicular to the y axis through this y coordinate and a line perpendicular to the x axis through this x coordinate, and they will intersect in the point P. So also, if we can construct x and y, we can, the point P with coordinates x comma y is constructible. So what I will do is I can change this from a one-way implication to an if and only if. So a point P is constructible if and only if its x and y coordinates are constructible numbers. Now let us see what happens at each stage of a construction. So at each stage of the construction, you've constructed a certain set of points and their coordinates would be constructible numbers. And now we can add a new point. The new points we are allowed to add are either intersections of lines passing through the constructed points, or intersections of circles with center at the constructed points and a radius which is constructible, or a circle and a line. Okay, so in each of these cases, let's see what are the new constructible numbers we get as x and y coordinates of constructible points. So here's a theorem. I'll call it theorem star. It's going to be used later. It's going to be important in what follows. So the theorem says that suppose I have a field extension f over q is a field. Now we look at three cases. If L1 and L2 are lines passing through points with coordinates in F, then the coordinates of L1 intersection L2 are in F. You don't even need to go to an extension. And B, if L is a line passing through points with coordinates in F, and C is a circle with center having coordinates in F and radius having coordinates in F. So maybe I should say center and, well, radius in F. Center having coordinates in F and radius in F. Then the points of intersection of L and C, there could be only one if L is tangential. Have coordinates in a quadratic extension of C, of F. And the last case is where you have if C1 and C2 are circles whose centers have coordinates in F and radii are in F. Then their points of intersection, again there could be just one point, but if they are tangential, their points of intersection lie in a quadratic extension of F. Okay, so part A is rather simple. What you have to do is, if you have 2 points, P equals x1, x2, x1, y1, and Q equals x2, y2, then this line L that passes through them its points will be given by an equation like if we have a point x comma y here, then what we know is that y2 minus y divided by, so we can assume that either x1 is not equal to x2 or y1 is not equal to y2. And now if I assume that x1 is not equal to x2, then I can write this like this: y2 minus y1 divided by x2 minus x1 is equal to y minus y1, x minus x1. If you want, you can move these to the other side and write it in form that doesn't involve any division, and so not have to worry about x equals x1 or x2 equals x1. And then from this you can show that if you have two such lines, then their point of intersection will lie in the same field, that it will just you can construct it by addition and multiplication of the coordinates of x1, y1 and x2, y2. So you'll have these kind of conditions for two lines. I'm going to leave this as an exercise for you and move on to the slightly more interesting cases of a circle and a line and two circles. So let's go to the proof of part B. So we have a point UV in the line L, where L is the line passing through x1, y1, x2, y2. And as I already explained, the condition for a point to lie on this line is that y2 minus y1 into u minus x1 is equal to x2 minus x1 equals v minus y1. And if we assume that, so we have to assume that these points x1, y1 and x2, y2 are not the same. So assuming that, for example, x1 is not equal to x2, if they are equal, then we have to use the fact that y1 will not be equal to y2. We can solve this and write v in terms of u. So v is going to be y1 minus y2 minus y1 divided by x2 minus x1 into u minus x1. And now if uv belongs to the circle with center, let's say, at x3 comma y3 and radius r, so this is the center and this is the radius, that's my notation, then what we know is that u minus x3 squared plus v minus y3 squared equals r squared. So what we get is that we can eliminate now, we can eliminate from this equation we can eliminate from this equation v using v equals this expression for v in terms of u. So eliminate v to get a quadratic equation in u. And so as we've seen, whenever you have a quadratic equation, its solutions lie in the extension of the field in which the coefficients lie by the square root of the discriminant. So uv, which implies that u belongs to f adjoint square root d, where d is already in f. And this implies that also v belongs to f square root d, because v can be written in terms of u by this equation here. So u and v both lie in f square root d. Now let's move on to the proof of C. We have a point that lies on two circles. So let's say u, v, the circles are the first one is with radius center x1 y1 and radius r1, and also it lies on the circle with center x2 y2 and radius r2. Then what we have is that this point u and v satisfy the equations u minus x1 squared plus v minus y1 squared equals r1 squared. This is equation 1. And u minus x2 squared plus v minus y2 squared equals r2 squared. This is equation 2. So now let's just add these equations, or rather maybe subtract these equations. So if we take equation 1 minus equation 2, then these quadratic terms will cancel out and we'll get a linear equation involving u and v. So what we get is minus 2u x1 minus x2 minus 2v y1 minus y2 is equal to r1 squared minus r2 squared. So using this we can eliminate, let's say assume that x1 is not equal to x2. Then we can write u as r1 squared minus r2 squared plus 2v y1 minus y2, the whole divided by x1 negative of x1 minus x2. And so you can eliminate u from either of these equations and solve for v. So substitute in 1. To get a quadratic equation. In v, and with coefficients in f. And so this implies that v belongs to f square root d, but then u can be recovered from v using this function here, so which also implies that u belongs to f square root d. And so u and v lie in a quadratic extension over f. So we have shown this theorem star, we have proved theorem star, which basically says that if at some stage of our construction all the points that we have constructed, their x and y coordinates lie in some field f, then any new point that we introduce at this stage of our construction, its coordinates will lie in a quadratic extension of f, or in f itself in case we are constructing the new point by intersecting two lines. But if a circle is involved, then it would probably lie in a quadratic extension of f. And now with this, you can kind of guess where all the constructible points come from. This is the statement, a beautiful theorem. We are now ready to prove. So a real number is constructible if and only if there exists a tower Fn containing Fn minus 1 going to F1 containing Q such that Fi index Fi minus 1 is 2 for I equals 2 to n, and also we assume that F1 index Q, the degree of F1 over Q is 2, and the number A belongs to Fn. So basically we're saying that constructible numbers are numbers that live in towers of quadratic extensions. Okay, so let's see how to prove this. So firstly, to prove it, we will first state a simple lemma which will make the proof easier to understand, that if every element of a field F is constructible, and E is an extension of F with degree 2, then every element of E is constructible. So this is taking care of one step of our tower. And proof? Well, we've already seen that if E is a quadratic extension of F, E is of the form F square root D for some D in F. Okay, now if we know that D is constructible, which implies that square root D is constructible. Okay, now constructible numbers form a field. And what we've seen is that this field contains F and root D. So it contains the smallest field containing both F and root D. So it contains E equals F root D. So every element of E is constructible. And that's the proof. So now we can prove this theorem in one direction, and which is that suppose A lies in a tower of quadratic extensions. So now suppose proof of theorem, if so firstly A in Q can be constructed. A belong to Q is constructible. Why is this? Every rational number is constructible because 1 is constructible, and constructible numbers form a field. Now so if 1 is in a field, then all rational numbers are in that field. So every element of Q is constructible. And now applying this lemma, so we have this, we have this extension fn minus 1 f1 over Q, and each of these is of degree 2. Each of these extensions is of degree 2. So now every element in Q is constructible. By this lemma, this implies that A belongs to F1 is constructible. So maybe I should say every A in Q is constructible implies that every A in F1 is constructible by this lemma. And that implies that every A in F2 is constructible, again applying that lemma, and so on, which means that every A in Fn is constructible. So you apply this lemma n times to show that every element of Fn is constructible. Now for the converse, we will have to use theorem star. So this shows that every element of Fn is constructible. Now we want to show that if we have a constructible number, then we can find a tower of quadratic extension, so that it lives in one of the fields in that tower. So for the converse, so if A in R is constructible, then it is the distance between two constructible points. Let's call them P and Q. So let's say P is x1, y1 and Q is x2, y2. So this means that the coordinates x1, y1, x2, y2 are constructible. Okay, so and so now this distance between P and Q, A is equal to square root of x1 minus x2 squared plus y1 minus y2 squared. So this is in a quadratic extension contained in these points. So this means that of course if these are constructible, then A is constructible. So it suffices to show, so A is in a quadratic extension containing the field containing x1, y1, x2 and y2. So it suffices to show that there exists a tower. Now to just save space, I'll write my tower horizontally. Fn contains Fn minus 1 contains f1 contains in Q, and each of these is of degree 2 of quadratic extensions such that x1, x2, y1 and y2 are in Fn. Okay. So now let's, so these points P and Q are constructible. So let's say that the construction of the points P and Q takes place through several steps. So suppose the construction of P and Q involves the construction of a sequence of points let's say P1, P2, Pn in this order, such that each Pi is constructed by joining either two lines in the previous step of the construction, or a circle and a line in the previous step of the construction, or two circles in the previous step of the construction. Then what we have is that let Fi be the field extension of Q containing, let's say that maybe I'll just say P1 is x1 comma y1, P2 is x2 comma y2, Pn is xn comma yn. Then if you look at this F, which is x1, y1 up to xi, yi, for I goes from 1 to n, then by theorem star, which we have here. Okay, so each of these points is constructed by intersecting two lines at the previous step, or intersecting a circle and a line at the previous step, or intersecting two circles at the previous step. So theorem star will now tell us that Fi index Fi minus 1 is either 1 or 2. And therefore, we have that the coordinates of P and Q lie in a tower of quadratic extensions. As claimed. Okay, a very interesting corollary of this is the following. If a number A is constructible, then you look at the degree of the extension QA over Q. This has to be a power of 2. Some non-negative integer r. In particular, A is algebraic, of course. This is because if we have a tower Fn minus 1, F1, Q, and each of these extensions is of degree 2, then the degree of Fn over Q is going to be 2 to the power n. It's going to be the product of these extensions. And now what we have is, if our element is constructible, then it lies inside some Fn like that. So Q alpha is an extension that is between Q and Fn, and so Fn q alpha q, this is 2 to the power n. So the only possibility for q alpha, the degree of q alpha over q, is that it has to be 2 to the power r for some r less than or equal to n.